Hi everyone. I wanted to do a video last week talking about the runtime complexity of Prim and Dijkstra. In the middle of doing it, I realized that it has been a while since we talked about binary heaps. And as you all know, binary heaps is the preferred way to implement a priority queue, and a priority queue is what's being used in these greedy algorithms to maintain their sense of what's the set of choices they have so that they could make their greedy selection. This time gap between our study of binary heaps and graphs was potentially getting in the way. So I thought I should do a little piece on that reminder, and then I should do an asymptotic complexity analysis of these two algorithms. All right, so this is the first one of the two, and I'm not going to be a perfectionist, so if my explanation, if there's a little bit of hum and mum, all that kind of stuff, I'm not going to do over and over again because I want to be able to send this out today. And I might also, I'm hoping that this thing is not going to keep failing on me, because that was the reason why I abandoned the pushing out these videos options, because my laptop keeps freezing after 12-13 minutes. So we'll see what happens. Quick reminder. So we have graphs like this, and we start our algorithm to find a set of edges, so that for a starting node, you end up having basically the selection of a subset of edges that interconnect everyone to everyone in the cheapest possible way. And what we realized was that in the cheapest possible way could be addressed from the point of view of the graph, or it could be addressed from the point of view of the starting place. So if you start here and you execute the algorithm called Prim, as it's considering this ever-growing horizon of the nodes that it has seen, if it's making its greedy choice based on an edge that is known to exist but yet to be marked, an edge who has the lowest capacity, lowest edge cost in that description would be the next one to be selected. So what I want to do is basically take that algorithm, have that algorithm take 2 steps on this thing, and then pause it, and then kind of connect it with our symbolic way to refer to a binary heap, because we used to draw it as trees with just integers, but then make it a little bit more real to give you the view under the hood, so to speak, of the adjacency list of that graph with an actual priority queue or a binary heap next to it, so that you can fully see the details. So before I execute a couple of steps of Prim running on this, let's make sure that we know how to turn this into an adjacency list. And I know we know, but we still want to draw a somewhat meticulous, we want to have a meticulous drawing of the adjacency list, because it's going to be instrumental in you seeing how the priority queue gets involved in the actual data structures of the algorithm. So 1, 2, 3, 4, 5 nodes, and I think 8 edges, 1, 2, 3, 4, 5, 6, 7, 8. So here are my 5 nodes, and these are the linked lists that are associated with the nodes. And as we all know at this point, I'm not going to bother drawing that. There's a map that, given a node reference, throws you to or associates that node with a particular list, and that list is called the adjacency list. And that list is indicating, starting from a particular node, what are the places you could go to. So that's why there are 3 things here. This is actually a linked list, because there are 3 edges here. So as far as B is concerned, there will be 2. That's why there are 2 here. This being a linked list, I'm terminating them. So if you look at C, it has 2 outgoing edges. That's why there's a linked list of 2 things. And then if you look at D, there's only 1 thing, so there's nothing there. It's just a null termination at the end. And E actually doesn't even associate with an adjacency list because it has no edges. So until we modified our graph data structures so that we could maintain these edge attributes or numbers or costs on these things, these used to point directly to the destination. So this edge right here would have been represented by a reference that is from A pointing to B, and that was the simplest way to do a graph data structure. But now that we have numbers on it, we felt the need to have these intermediate objects to carry all that information we associate with the edges. So we said that, okay, we will have an edge class. An edge class will be basically 2 things. So I'm going to draw them like this. One of them would actually point to the destination. First, let me actually draw the boxes here. So these will not necessarily point to the destinations, but they point to these intermediate edge objects, and those edge objects in turn point to the destination. So I'm going to assume that the second of these pair these objects that have a pair of fields in them. The second field is the destination reference, so A points to B, C, D. So here's B, it points to C, and then it points to D. Okay, so we have to do the same thing for B. So B points to C and E. So this one is going to be easy. This one's going to be a little windy. It points there. And then C points to D and E, the last two. So points to D and E. And that, oh, and then D points to E. So there's this one last one. Like this. So if you were looking at it from a topological sort point of view, the one that has the highest incoming edge counter would be E, even though it has nothing pointing out of it. Okay, now the one thing that I haven't done here is that we created these intermediate data structures called edges to carry the edge attributes, but I haven't put them there. So I'll do that now. So A to B is 2, A to C is 4, and A to D is 6, and then B to C is 5, and then B to E, B to D, no, B to E, sorry, I confused myself, and that actually is a 3, and that's a 5. And then C to D is a 5. And then C to E is a 9. And then finally D to E is 11, the most expensive one. Okay, so this is the deal, and there are times where I have drawn these things as so, and I said, like, let's draw them as a list. So if you have like a Java list, which we typically draw it as a queue, so you can imagine that these things are actually located inside these things. Although this is not that important for the comprehension of it, it's just visually sort of maybe making it look a little nicer. And as I said, these nodes are associated with these lists by the use of a map. So let's run the algorithm, and I'm going to use the green one to express where we are. So if I start Prim's algorithm from A, it says, good, I have seen A, and according to the horizon that I have access to from the starting point of A, basically this is as far as I can see. Now, when I say this, remember that we are always considering the number of arrows crossing the horizon from our side to the other side as a quantifier for the number of things you have in the priority queue. So it says 2, 4, 6, picks the cheapest one, and then it picks this. Okay? And right here, we want to stop it and say, we have seen this. Basically, that is processed. We no longer have to deal with that node. We have actually selected this edge, and we also have seen this. So as far as Prim's execution is concerned, at this point, 2 nodes as well as 1 edge has been processed. I want you to keep in mind that it is always going to be the case that if you count the number of nodes that have these check boxes or check marks, those nodes with the check marks will be 1 greater in number than the number of edges that you have selected. Because remember that the purpose of these algorithms is to select a subset of edges in the topology of a tree so that everyone directly or indirectly can get to anyone else, but there's nothing extra, there's nothing superfluous. So for that reason, the number of nodes with these will always be 1 greater than the number of edges, because if you have X number of things, you need X minus number of things to put them in contact with each other directly or indirectly. So at this point, if someone says, what does the priority queue look like? Well, so you could say, in the priority queue, which I'm going to be assuming is using a binary heap, initially there was 2, 4, and 6. So let's say that as it was populating its priority queue, it went from 2, 4, 6 in that direction. So here's the 2. And then the next thing that arrived was a 4. And then the next thing that arrived was a 6. So this was the state of the priority queue before it did this selection and proceed. So at that point, remember that Prim said, now that I have put in all the edges that I'm yet to process, the ones that cross from my side to the other side of the horizon, give me the cheapest thing. And what the priority queue did was it took the 2 out, so 2 just was taken out. That's why we ended up going here, because we selected the edge associated with a cost of 2. But then at this point, we had a gap here. Now you have to stop thinking in terms of a graph, and you have to start thinking in terms of a binary heap. Remember that those things were supposed to be perfect triangles. Even an ADL tree was way too imbalanced. A binary heap is perfectly balanced. And also it all fills up from the top to the bottom. And here you are, the least element in it, which had the highest priority, has been thrown out, and there's a hole there. So what do? You put the 6 here. And then you realize that so this is higher than its child, so it swaps places. So this ends up being 6. This ends up being 4. So as of the step of using this, the priority queue, the binary heap, has been reduced to this state. So what I'm going to do is I'm going to say, let's actually do this, because that's too much details. In reality, not in reality, but in the cleanest possible way of drawing it, the binary heap, which we visualize as a tree, is in this format. So if I were to say, give me the next thing, it will give me 4, because 4 is less than 6. And that's always the way it's arranged. But the thing is, when you went in this direction, you put new things on your horizon. So the 4 and the 6 are still there, but now 3 and 5. So let's put the 5 in here. Let's actually put 3. I don't know which one is better. Let's put 5 in here. 3 in here, sorry. So I don't know how many times that was. So basically, so the 5 comes here, and it instantly is okay because 4 is greater than the 2 children, so it doesn't have to do anything more. But then the 3 has to come in now. So remember that you always go to the bottom. So if you are at a level at the bottom with some space on the right side, that's where the new things come in from. But if you have fully saturated the last one in the priority heap, you go on to the next one. So here comes 3. So the thing is, like, it's not happy here because it's supposed to be the lowest, but it's at the bottom. So what it does is it says, all right, I'm going to actually swap places. And still the case that it's not ordered properly. So that means that if I were to redraw this, I would say, here's my 3, here's my 5, here's my 4, and here's my 6. So the binary heap is in this state. Now, you have to keep this in mind as we do the asymptotic complexity of the algorithm, because look what it took for me to take something out of the priority queue and for me to make new additions to it. I had to do an operation that is that many steps. So we will say, as the greedy algorithm is taking something out of the priority queue, it's going to have an operation that is proportional to the height of the tree, which is going to be log base 2 of the number of things in it. And every time you're adding something to it, it's going to be the same thing. The operation that you do to add something to the priority queue will be log base 2 of the number of things in it. And we will oftentimes ask ourselves, well, how many things are there so I can make that be a specific number? And that's where you have to kind of associate it with the algorithm, but we're yet to get there. So as the algorithm Prim is moving forward, what you have to remember is that there's a horizon. There are these lines crossing from our side of the horizon to the other side. Every time there's an intersection of these arrows with the horizon, that implies a particular element in the priority queue. And when you do in queue and dequeue to the priority queue, based on the operation of the binary heap data structure, the cost of that operation will be proportional to exactly the log base 2 of the number of things in it. So finally, before I wrap up this video, what exactly does this look like when you see some realism to it? Because again, this was in the abstract, but let's make it real, because this is the adjacency list. What does the priority queue look like? It looks like this. I'm going to use, what color should I use? Green, black. How does this look as the real thing? It looks like this. Notice that I didn't put the numbers in there because the numbers are not there in reality. So the top 1, 3 was a reference to this edge, right? So this edge right here goes with node B. Here's the 3. Okay, so this right here, I'm going to use green. I think green's going to make it different enough. It's pointing to that. So the next one was 4. 4 is this, so that's an edge. So this one right here. It's pointing to that. This one was 5, and I think it's this 5, which is B pointing to E. And okay, so this one points to this. And finally, this one was 6. What is that 6? That's the edge from A to D. It's this one. So this is how it is actually in memory. This was a mathematical and visual way to explain the operation of a binary heap, which is the engine that powers the priority queue. But because we have done this in Java, now you should be able to wrap your minds around the way that it actually is happening, which is this graph right here is realized as this adjacency list. And when you couple an algorithm's priority queue with that adjacency list, the entries in the priority queue are not copies of these numbers. They are references to the edge objects that the edge values are contained in. If this class is implementing the comparable interface, that means that this class has a compare to method. So when, if we were to say that, okay, give me the next minimum one, this gets taken out, this gets put in there, and it does its priority queue business as that percolating up and down, depending on whether you are small or not, depending on where your position is. All of those decisions are being done as a consequence of calling the compare to method of the edge class, which is looking at the edge values here and able to make the cheapest one sit at the top, and then when prim is working, that's basically what it's using. Now, if you actually extend this to Dijkstra, basically you just have to invent one more object that for each edge that it would have put in the priority queue, it actually puts a path object instead of an edge one, which ends up being the associated edges cost plus the path cost from the starting place to the node where that edge is anchored. After that, the same greedy algorithm works. Okay, so I'm going to move on to the second one, which is going to be doing the asymptotic complexity of prim and Dijkstra. And I think that was what I tried to do on Friday. Hopefully this is going to work.